Okay, let us solve this problem based on kinetics. A first order reaction A to B requires activation energy of 70 kilojoules per mole when a 20% solution of A was kept at 25 degrees Celsius for 20 minutes. 25% decomposition took place, and what will be the percentage decomposition in the same time in a 30% solution maintained at 40 degrees Celsius, assuming that the activation energy remains constant in this range of temperature. Now here we have a first order reaction of the type A to B, and the energy of activation is a 70 kilojoule per mole. You know that the energy of activation for a given reaction remains constant, and for a first order reaction, the time required for a definite fraction of a reaction to be completed is not depending on the initial concentration. That you have to remember. And as the temperature changes, we know that the rate of a chemical reaction also changes, and the rate constant of the reaction also changes with temperature. Now let us assume that at 25 degrees Celsius, K1 be the rate constant of a reaction. Here T is equal to 20 minutes, and X is a 25% decomposition takes place in 20 minutes. So X is equal to 25. Now let us take initial concentration as 100. A minus X is equal to 100 minus 25, that is 75. Now let us try to calculate the K1 value for this. K1 is equal to 2.303 upon T log A upon A minus X. So T is 20. Initial concentration is taken as 100. A minus X is 75. Calculate. This is step 1. If you calculate, it is 0.01437 per minute. In this way, we have to calculate what is the rate constant of a reaction at 25 degrees Celsius. Now, when we change the temperature to 40 degrees Celsius, do you think that the rate constant remains same? No. Rate constant changes with temperature. Now, let us calculate the K2 value at 40 degrees Celsius. Calculation of K2 at 40 degrees Celsius. This is step 2. We know that K1 is equal to 0.0438 per minute, and it is given that the energy of activation of a reaction is 70 kilojoule, so it is 70,000 joule. Initial temperature 25 degrees Celsius, convert it into Kelvin, 298 Kelvin, and T2 is 40 degrees Celsius, convert it into Kelvin, it is 313 Kelvin. Now you calculate K2. Now if K1 is known, how to calculate K2? When temperatures T1 and T2 are given, you can use Arrhenius equation of energy of activation. We know that log of K2 by K1 equals EA divided by 2.303 R into T2 minus T1 divided by T1 T2. On substitution, EA is 70,000, 2.303, R value 8.314, T2 313, T1, substitute all these values and get log K2 by K1. Log K2 by K1 is 0.5854. We got log K2 by K1. Therefore, K2 by K1 is antilog of 0.5854. You see the antilog of this? It is 3.849. Therefore, K2 equals K1 into 3.849. Put the value of K1. We got K1 in step 1. 0.01437 multiplied by 3.849. That is 0.0553 per minute. This is second step. We got K2. Here we got K1. Now why we need K2? Why we need K2? Because the reaction, how much of the reaction is completed at 40 degrees Celsius. To know that, we should know what is the rate constant at 40 degrees Celsius. For that purpose, we have calculated K2 value. Once you know K2, you put this equation K2 equals 2.303 upon T log A upon A minus X. So time, in the same time, what percentage of the reaction will be completed? So time is the same. It is 20 minutes. 2.303 upon K2. K2 is 0.0553 into log of A is 100 upon 100 minus X. We don't know the value of X. How much is reacted? We don't know. 100 minus X. So log of 100 upon 100 minus X is equal to 20 multiplied by 0.0553 divided by 2.303, that equals 0.4802. I want 100 upon 100 minus X. 100 upon 100 minus X is antilogarithm of 0.4802. Antilog of 0.4802 is 3.0213. 3.0213. Therefore, 100 minus X is equal to 100 divided by 3.0213. That is equal to 33.098. This is 100 minus X. Therefore, X equals 100 minus 33.098. It is equal to 66.902%. Why do you take it as a percent? Because initial concentration is taken as 100. Initial concentration A is taken as 100, and out of that 66.902 will undergo dissociation or undergo reaction. Therefore, it is out of 100. Hence, it is in percentage. Therefore, X is equal to 66.9, nearly 66.9% of the reaction is completed in 20 minutes. This is how we have to solve the problem based on